Okay, I have another conduction demo here. This metal star has got pins attached to the ends of each of these bars using wax. Each bar is made out of a different material. What I'm going to do is to heat the center here. We're going to see the heat being conducted along each bar. When it gets to the end, it will cause the wax to melt and the pins will fall. If we go ahead and do that now. So, just a reminder, with conduction, the particles closest to the heat source are gaining kinetic energy. They are vibrating more vigorously. They are then colliding with their neighbours, causing them to vibrate also. With metals, there are free electrons within the material that are able to move freely, thus transferring that kinetic energy. We've seen that the 2 pins have already fallen, so that wax has melted. Those 2 are obviously the best conductors. We've just seen another one fall now. The 2 that are remaining are the worst conductors. The difference in conduction is due to a difference in the number of free electrons present within that material. Hopefully, if we leave it a couple more seconds, we should see that the other 2 melt and those pins fall. There we go. So this tells us A, that conduction is taking place, and B, that different metals conduct thermal heat at different rates. That last one is obviously the worst conductor, so therefore has the least number of free electrons within the material. Just a reminder that silver is going to be the best thermal conductor because it has the most free electrons per unit volume. This last one obviously not a good conductor because that pin has still not fallen. We're having to raise it to a significant temperature. The heat is obviously not finding it particularly easy to move through that bar down to that final pin. There we go. So clearly this is the worst conductor. I think this was the first one that fell, so that tells us that's the best conductor. Hi guys, this is a Leslie's cube. It's a metal container that has different surfaces on each face. So the 2 that I'm going to concentrate on are this one, which is a black matte finish, and this one, which is a white shiny finish. Now what I'm going to do is fill this with water that has been freshly boiled. Now, because each of the faces is made from the same material, we know that the heat is going to be conducted to the surface of each face at the same rate. So if we were to be able to measure the temperature of each face, we'd find that it's exactly the same. All I'm going to do to start with is place my hands either side of the cube, and I can very distinctly feel that this hand, the side that's next to the black matte surface, is significantly warmer than this hand, which is next to the white shiny surface. Now, let's think about how this heat can be getting to my hands. Can it get to my hands via conduction? The answer is no. Why? Because air is a very poor conductor. Remember, the particles in air are very far apart, and so they are unable to transfer heat effectively via conduction. One particle vibrating here is not going to collide with another one vibrating here and pass that energy on. It does happen, but very, very slowly. So we've ruled out the heat getting to my hands via conduction. Can we consider convection? Well, what happens with convection is the air becomes less dense and rises. So would that heat be being transferred laterally? No, it gets transferred in the vertical direction only. And seeing as the heat is getting to my hands in a sideways direction, we can rule out convection. The only way the heat can be getting to my hands is via radiation. Now that's being transferred by infrared waves, which is part of the electromagnetic spectrum. Okay, so what I'm going to do is actually trying to quantify this now. So me holding my hands here and saying, well, this is warmer than this one. Obviously, we're looking at that qualitatively. I want to now look at it quantitatively. So come back to me in a couple of seconds and we'll have a look how we can do that. So we're still with the Leslie's cube. We've already looked at this qualitatively. So I've said that I could feel more heat being emitted from the black matte surface than I could from the white shiny surface. But now I want to look at it quantitatively. What I've done is connected two infrared sensors to our data loggers, and using this this wooden block, I'm going to make sure that they are both equidistant from the surface. That's one of our control variables. Now what we can do is we can have a look at how much heat is being emitted from each surface. The black matte surface is emitting 133.3 watts per meter squared, whereas the white shiny surface is emitting 10.11 watts per meter squared. Clearly, we are having more thermal radiation being emitted from the black matte surface than we are from the white shiny surface, despite the fact that they are at exactly the same temperature.